Whether we like it or not, we now live in the age of
AI,
where large language models are gobbling up all of the compute resources and attention of policymakers and financing and the stock market and everybody, and it's all we ever hear about and it's all we ever see. And YouTube is just the LLM produced AI slop that is just outpouring. And many of us are wondering, what is the point of all of this? Is this what we should be using this raw intelligence for? No, we should be using it for science. And one of the most data hungry, data producing fields of science that is out there is astronomy, when you've got these giant survey telescopes that are taking pictures of the sky, producing enormous amounts of data. And up until now, postdocs and grad students have had to carefully and slowly go through these data to look for interesting things, interesting galaxies, gravitational lenses, things like that. But it turns out that these large language models are actually not terrible at looking at a picture of a galaxy and identifying interesting features. They are aware of the literature, they've seen lots of images, and they maybe be able to help out with science. And I think that would give them a good job. So my guest today is Nolan Koblischke. He is a PhD student at the Astronomy Department of the University of Toronto, and he's a member of the Polymathic AI collaboration. And he has been seeing if the modern large language models like ChatGPT, like Google Gemini, can evaluate astronomical images and pick out interesting features, the kinds of things that astronomers would use to do follow-on studies. He's built a search engine. He's taken 300,000 images, fed them into ChatGPT. It has evaluated them, given text descriptions of what it sees in those images, and then he can now search through all of those images to find gravitational lenses and tidal tails and edge-on galaxies, things that might be interesting to astronomers, and has been thinking a lot about sort of what role this technology might play in science. And so if you're wondering if maybe somebody has come up with a good use for this technology, I think you're going to enjoy this conversation with Nolan Koblischke. Nolan, you have been evaluating various LLMs for their ability to be astronomy assistants. So far in your experience, which one has the chops?
Yeah, well, particularly, I was most recently interested in how well they can actually look at an image of a galaxy and describe the phenomena occurring in that image. And what I found is that the current models that are the best at this are from OpenAI and Google. And so these models have been trained on the whole internet when it comes to language and also the images that occur on the internet. And so they actually have a surprisingly good ability to describe phenomena in galaxy images. Unfortunately, there's also open models that I can run on my GPU, but these aren't up to par yet, although this is like an active research area. So specifically when I go to what are the most cutting edge models? It's those from OpenAI and Google.
But that's interesting, right? That just a generic model that will give you a recipe for the raw ingredients that you have in your kitchen, or write your college essay, also has the underlying skills and capabilities to identify features in a galaxy image better than something that you custom trained using your own GPU resources.
Yeah, exactly.
That's bananas.
I know, right? It's crazy. So I think that this is a result of just the scale of data that went into the model. So I could, and astronomers have cooked up their own models that can classify images of galaxies. But say, for example, there's like a weird arc in the corner of the image, or something to that accord. Like these massive models from these companies have been trained on all the literature. And so this is where I think they have the best advantage compared to much, smaller models that were for specific tasks, is these massive models like, say, GPT-5 can actually understand that, that weird arc in the corner could be indicative of, it's able to spot it and it's able to like relate it to, its literature knowledge, for example. And so this is a big advantage that it has.
And so I sort of imagine, my experiences in training models, they fall into these local minima where, you show it a cat and then you show it the reverse version of the cat. It's like, I don't know what's going on here. I have no context. What is this? And yet with these large models, they're now, I guess, multimodal by kind of default. They've been trained on images, they've been trained on videos, they've been trained on literature, and that you're getting these emergent behaviors where it's able to look at something with a little bit of knowledge. Do you have to like prep it? Do you have to do some multi shots to go, okay, here's what we've learned in the past. You might see stuff and that could be an arc and that could be, some transient or whatever. Or do you find it just raw, straight up? What do you see here?
Yeah, so this is another one of the big advantages. The first one that I alluded to was that, unlike any other model that we've, trained, it, has read all the literature. And so it has a much better understanding of what might be scientifically interesting. And the second big advantage I see of these foundation models is that you can just throw them at any task and see how they do. I'm not going to guarantee that they're going to do amazing, especially as you said, zero shot, which means that we don't give it any examples. But for example, if you have, if you're trying to find galaxies with streams of stars that orbit the galaxy, which is something I'm particularly interested in to study dark matter, this is a phenomena that typically, if you want to find these cases out of 100 million images of galaxies, I would have to go out and actually like label, and try and find a few hundred of them, and this would take weeks and weeks of my time, and then I would have to train a model and run it over 100 million. But with these foundation models that suddenly are becoming a lot more generally, they're getting a lot more general abilities to understand images, even in astronomy, you can just throw it an image of a galaxy with a stream and say, hey, does this have a stream? Yes or no? And it's not going to be perfect, but it's going to actually, have a chance at attempting this task and classifying these galaxies just off the bat with no additional data.
One of the experiences that I've had, and I think people have sort of seen this too, is this sort of idea of sycophancy, that the models kind of they'll try to do what you're asking them to do, whether or not that's. And so like I find if I'm going to ask it for a direction, I have to be really careful not to even give a hint about which answer I would prefer, because then I get the answer that I might be sort of I'm just, it's just going to reinforce my existing bias. Have you sort of experienced any of that with this process?
Yeah, actually, I think I do have some evidence for this in the case that, so in my most recent paper, we got these language models to write descriptions for 300,000 around 300,000 images of galaxies. And the descriptions were meant to be completely general. And the reason why we did this is to build like a search engine for eventually like 100 million images based, purely off text, which is a total new ability. But when we went about making descriptions for 300,000 images, getting it to write these descriptions, we had to prompt it. And so we would prompt it with stuff like, hey, make sure to look out for example, gravitational lenses.
Right. Oops.
And so what I found is that it was actually very eager to label something as a gravitational lens. And so this is stuff that you have to watch out for.
Interesting. So it's more accurate if you don't tell it what to look out for than if you start to give it some slight nudges of the kinds of things that would be scientifically interesting to you.
It's a form of bias, I guess. Like if you include, AGN, active galactic nuclei, or star forming regions, if you include these in the prompt, hey, make sure to look out for them, then the model is going to have that in its. I'm being very, I'm kind of humanizing it, but it's going to have it in its mind, and it's probably going to be a lot more likely that it's going to include it in the description. So that's something to look out for. Yeah.
Yeah, that's interesting. And like this is a behavior that wouldn't have occurred to me I don't know, a year ago.
Yeah.
But now I think this sycophancy is a behavior that we're becoming so familiar with, and until they've sort of solved this problem, you have to be on high alert that unless you are really careful about how you pose your queries to the LLM, you're going to get kind of what it's going to show you a mirror. Would gladly show you a mirror
Yeah.
before showing, coming up with any original idea of its own. That's really interesting. So explain to me this process then. You've got where you're getting your raw data from, and then how are you sort of preparing it and submitting it to the LLM and then getting your data back?
Yeah. So essentially, the problem statement here is that we have these data sets of, hundreds of millions of images of galaxies. Um, and we want to be able to find interesting things. For example, like I talked about galaxies with streams of stars that you can actually see in the image that's orbiting the galaxy, which is useful for dark matter. Maybe gravitational lenses you want to find where a galaxy is bending the light of one behind it. And these, occur 0.1% or less of the time in 100 million images. And so currently, to be able to search for them, it's very laborious. You have to go and actually look yourself, or you have to look yourself, label a set and then train a neural network to go and find it. So it takes weeks or months. So our goal was to build a system where you can just type in text what you want to find. So you just write a description, galaxy with stream, and hopefully,
Yeah, show me an Einstein cross, please.
yeah, exactly.
Yeah.
Hopefully these pop up.
Yeah.
And so in order to do that, you would need a data set with images and then their associated descriptions of those images. And this doesn't exist. It didn't exist until we found that language models like GPT-4 at the time actually could write half decent descriptions of the images. And so we use that to just generate, as I said, like 300,000 descriptions of 300,000 images. And right away, you could search this now by finding, what description is closest to your query. So it's most similar to your query of Galaxy with Stream. And so you could search the 300,000 right away. But to then expand this to, say you want to search 100 million images, we had to do some training of our own model. And so this specifically, what we did is we took these 300,000 descriptions and used it as a training set to then say, hey, I want to be able to find, the most similar galaxy to my text query, rather than the most similar description. Because if we were to generate descriptions for 100 million, it would be very costly computationally, or if you're using these models from a service, then financially costly to write descriptions for 100 million. And so we used what's called contrastive learning, which essentially is when you take an image and a piece of text and you train a neural network to put them into a very similar representation in a space. And so what that means is you have numbers that describe the phenomena in the image. And so if you can train a model to make the images and the text aligned, then what you can do is you can then, run this model on, 100 million images to generate these representations. And then what you can do is you have a new text query. So you have, 2 edge-on galaxies. What you then do is you find you can use the model to then make a representation of that text query and find the most similar images to what you're trying to look for.
Right. And so the traditional way of doing this is that you would have some poor grad student who would sit down and look at images and slowly, laboriously describe each image, set it aside, grab the next one, come back
Yeah.
a month later and they've got 10 of them, and you give them, you say good job, and then you start to use that to train. And so instead the question is, can you just turn the raw intelligence of one of these LLMs on this problem, create a much larger data set, get those descriptions, use that to train your model on the larger data set, speeding up the whole process and hopefully getting a good description of the other side.
Exactly. So now if you want to find, like I said, two edge-on galaxies in the same image, you don't need to do a month of labeling anymore to then train a model to go out and find it. You can just try and type it in the search engine and see what comes up. And we find that I'm not going to claim it's perfect, but it's a lot. It's pretty amazing what actually can show up. So actually already
Right.
I've found like galaxies with streams, many of them actually from this search engine.
And so are you looking to, you have this, say how much is it, 300,000 you said was the sort of the raw list. And you're like, oh, we've got two edge-on galaxies in this one. And you're like, all I care about are edge-on galaxies. So I'm going to train my neural net on the ones that qualify to having edge-on galaxies, so that it just gets super good at finding edge-on galaxies. And then I compare that against the 100 million. And because it's such a relatively simple query, then boom, I get a large number. And then I can use that as my starting point for doing follow-on observations with the telescope and whatever. Or are you you training them at a bunch of things at the same time to kind of get a better evaluation of the of the 100 million images?
Yeah, so we actually went about this trying not to bias the training set at all. So we didn't curate it to we didn't purposely put in gravitational lenses in the training set and tell the language model, hey, here's a gravitational lens, write a description for it, for example, because then the search engine would be great, or hopefully a lot better at finding gravitational lenses. However, if someone is interested in something else, then they wouldn't get much use of it. So what we did is we just randomly chose 300,000 and just tried to make very general descriptions so that our search engine could be general enough, because we don't know what people are interested in and we can't tell what they're going to find with it.
Right. But I guess what I'm saying is that when you're using, say, even GPT-4's image analysis capability, you're having to pay those API costs. It's expensive to even, I'm sure your university got a bill for 300,000 images, and they were like, we need to pay what now?
$150.
How much?
$150. So
that's not bad.
Yeah. This is with GPT 4.1 mini. And so we actually tried to find the most cost-effective model. However, I would love to have the money to, write descriptions for 100 million. And that would be tens of thousands or more.
Yes.
Yeah.
But that's not a ludicrous amount of money.
Yeah.
But I'm sure you've then done the same math and going like, if I use 5.2, what would that get me? Or Gemini 3, right?
Yeah. It can then get a lot more expensive than the smaller models. But yeah.
Yeah. Yeah. And so, but I guess I sort of was imagining you getting that initial set as like a bridge that would then let you train your own neural network that does exactly what you need and doesn't care about anything but galaxies.
Yeah.
Right.
I think this is absolutely what people should do. Once they've found an initial few of what they're looking for, then you can go out and train your own model to go out and find them. And actually, with astronomy data foundation models, you have a much better starting point at, you can actually fine tune them on whatever you're trying to do. So if you want to be more involved and you want to actually, conduct a very extensive search for galaxies with streams, that's not just typing it into my search engine, you can collect potentially as low as a few dozen and try and use a astronomy foundation model like the one that I actually used in my paper called AION, which has already been trained on hundreds of millions of images. And so it's already has a pretty good physical understanding of these images. And you can fine tune that for your specific queries of interest, which would be a much more systematic way to go about and actually search for these things, where my search engine is to, find things that you don't have these large data sets for. Yeah.
So did the model find things that were unexpected that actually turned out to be real?
Yeah. So this is the kind of goal. So I think you asked me earlier, is it just chatbots that are helping out in astronomy? And chatbots, I think, have really been a huge productivity tool for like finding literature and also for coding. But the whole goal of, my research going forward, and this was the first example, is actually using these language models for discovery purposes. And so this is different than chatbots in that I actually want to integrate them into the pipelines. So writing a description for every galaxy image that comes out of a pipeline is kind of the first step in, potentially some of these images it might find quite scientifically interesting. And because it's read the literature, and because it's read all these papers, I think it has the best chance of any automated system we've developed of determining if an image is actually scientifically interesting. And so there has been phenomena that I've found with the search engine. For example, galaxy. I know I've mentioned galaxies with streams a lot. This is just what I'm focused on, but ones that look, unlike any other that I've seen. And I'm not an expert enough to see how big of a discovery this is. I'm not sure, but there's certainly been a lot of images where I don't know what's going on. My supervisor doesn't know what's going on, and so we saved the link for these. This is an ability in the search engine to just copy the link for these individual images, and we're probably going to look them up further.
But how does the LLM sort of express curiosity and novelty of an image to you through the search engine?
Yeah, so with the search engine explicitly, so we built it such that we don't need to be generating these descriptions with an LLM during the search. However, there is a feature that we tested out in the paper that's not on the search engine, which is that after a search is completed, for example, I'm trying to find two edge-on galaxies or something like this, you have, the top 10,000 results. And you have to, if it's a rare object, you have to manually scroll and look through all of them individually. So there's a feature that we developed called LLM re-ranking in our paper, where we have a language model like GPT-4 or GPT-5, and we have it look at each image individually, and we can ask it a question. So we can say, hey, is this actually a galaxy with a stream? Rank from 1 to 10, and also write a description about what you think about this image. And we can actually run it and have it go over all the top, 1,000 results, and then reorder the list such that the most interesting images, most relevant to our query, bubble up to the top of the list.
But that's kind of going back to what we talked about before. You're essentially running a new query on the API, having it look at this image with fresh eyes. You're possibly skewing the results with it being sycophantic, and yet you're saying, even despite that, interesting images are popping to the top.
Yes, totally. So it's we have the evidence that this actually increases the amount of like true in our test gravitational lenses in like the top 10 results and top 100 results. Like it can actually bubble up the most interesting images to the top of the list.
Right.
Despite any biases. Yeah.
But right now, I guess back to my original question is, has there been a situation where the LLM has gone, oh, and I think I see a cosmic string, right?
Yeah.
Where it knows the literature, you're not giving it any specifics on what to be looking for. It's going, I see a galaxy, I see a galaxy, I see a star, blah, blah, blah. And then goes, oh, I think I see a cosmic string. And there is a quark star.
Yeah, so this is the dream, really. We haven't. I think this is an active area of research, so I don't have like a strong example for you right now. I think the most difficult part about this is like we could run GPT-4 or GPT-5 on all of the images coming from our pipeline and ask it to point out the most interesting ones and why it's most interesting. The hard part is evaluating at that point. Okay, you have you know out of my 300,000 descriptions, it might have pointed out that some were extremely interesting and that it found a new discovery. But to actually evaluate if it is a new discovery, I would need to request, follow-up time with the, Hubble Space Telescope or James Webb, and it would take a year, and I would need to reach out to experts, that are specific in that area because it might not be the area that I'm focused on to actually go and see if it's found something interesting. And so I can't guarantee that it has found an example like this because it just takes so much time to follow up on these things.
Right, but has it tried to?
Yeah,
Has it freaked out and said, "I think I see aliens here"? Like I would love to know what it thinks it sees and sort of your level of skepticism when you look at the thing, when it's, when it's
so
really putting out an alarm and you look at it and you go, "Come on, that's just a cloud.
yeah,
That's just a bird."
so this is classic hallucinations, is what they call it. And so we have found, actually, we built a benchmark to actually evaluate these descriptions specifically on like a subset of like 64 galaxies where we have good labels on like stuff like how many spiral arms are in a galaxy. And there might be, the ground truth answer is that there's clearly three. But the model will say, oh, there's two spiral arms, and there might be it could be undergoing a merger, or like it sees clusters of galaxies, together, and it says, oh, these are all gravitationally lensed galaxies, when this is probably not the case. And so it has these hallucinations quite often. And so you have to be skeptical. So this is another reason why, like, you're entirely right. If it goes out and declares a discovery, I'm not going to believe it. I'm gonna have to yeah, create some kind of filtering step, or this is where you actually still need the expert time to actually go over everything that it says, oh, this is interesting, actually see if it's interesting, because it's currently not at that level.
Right, of course. But I feel like that's sort of like the next step, is that it unprompted, and like I think this is the key, is you don't say, do you see any aliens? Because it'll go like, yeah, I see aliens all over the place. The truth is now being revealed, and we need to take this to the authorities. So I think you're not giving it any prompt, you're not giving it any hint of what you're saying, and it to out of its own sort of just like, yes, I will look at pictures of galaxies and tell you what I see. I am an astronomer, right? That it will go like, wait a minute, I just found something really weird, I think, and I know the literature, and I think I found this thing, and I think I might have discovered something, and hey, advisor, take a look at this. What do you think? And have there been any examples where it's said something that's made you go, I really should look at this? And then you look at it and either go, no, that's ridiculous, or you're like, I don't know, I'm going to need to talk to an expert and put it into an expert pipeline. And hopefully the experts don't think I'm a crank, right? Like that's the risk, is you keep going back to them going, hey, supernova expert, here's a bunch in one galaxy. And they're like, you don't know what you're talking about. Please stop calling.
Yeah, I've definitely had a lot of the first case where it declares to have found something, and then, most of the time, or almost all the time, it's not the case. Like I said, with gravitational lenses, there has been cases. So if you want explicit cases, I told you I'm saving like interesting results from the search engine. And there has been cases where it looks like it's described some images as gravitational lensing, and from my eye, it actually does look like it. And so these are ones that I actually am sending to the experts in those fields. And I've looked in the catalogs, and these two images have not been confirmed as gravitational lenses. And so, I'm not going to say that they are. Um, like you do need a follow-up to actually confirm, but it looks, like it actually had it on the nose there, and that these are something that, deserve follow-up. Yeah.
So theoretically, and I'm like, well, I'm not going to put you on the spot here, but
Sure.
theoretically, giving the LLM a sort of non-biased, take a look at this picture, tell me what you see, it is theoretically describing features which are important to astronomers, like gravitational lenses or tidal tails or whatever, that were previously unknown in the existing astronomy literature and databases as the known gravitational lenses, that each of which were found by poor grad students who had to spend weeks and months at this, turning up potentially more of these things that, upon a cursory look by a person who is not specialized in this but kind of knows what astronomy stuff looks like, confirms that maybe there is something real here, and maybe that there are new additions to be made to the catalogs. Do you think that's a sort of nuanced position?
Yeah, I think that's a totally good nuanced position.
Yeah.
Gravitational lenses are becoming a lot more, common. Not common, but like we're finding a lot more of them. Like, I think last year there was this one survey that found like 500 strong lenses, and there's going to be hundreds and thousands more in the future.
Yes.
The hard part is like, it works as a classifier. The cool thing in the future that I'm really excited for is if it's able to find something that, would actually contribute to the literature.
As a type of object or phenomenon that's never been seen
exactly,
before.
Exactly.
Right. Yeah.
But this is probably the most difficult challenge for these models and for humans. So there's going to be a lot of work that would go into that.
Yeah. I mean, I think the sort of the common complaint about these LLMs is that their ceiling is human capability, that they can never do better than whatever they've been trained on. They can never do better than whatever is the best thing that that humans have seen so far. The writing, the music, all of that is always just sort of capped at what is the blended goulash of human knowledge. And the hope is that it can actually participate in actual increased scientific knowledge. And sort of the one way is that they could make better insights and go, for some reason, I've gained this power to be able to look at this astronomy image and spot something that a regular astronomer wouldn't know, because I have a broader knowledge of the literature and I know, the weird things that people have proposed that nobody's ever seen before. That would be amazing, right? But plan B is they just are willing to do the scut work day after day after day, look at 100 million images and just properly categorize them in a way that maybe astronomers don't have time to do that. But I think, it's a good time because there are entirely new new systems coming online right now. Vera Rubin, we're days away from it entering operations and just disgorging petabytes of data onto the internet. You've got Nancy Grace Roman, which has completed construction. It's coming out very soon. You've got Euclid. You've got massive astronomical databases that nobody will have peered at a teeny fraction of it. Robots have got to be our only way to get through this.
Yeah, I absolutely agree. And this is why I'm so excited about language models as the potential solution to these, or one part of a potential solution to this massive data problem. Where, wouldn't it be great if we had some eyes on all of the data coming in from Vera Rubin, as you said, I think there's going to be something like 10 million alerts of things changing in the night sky per day from Vera Rubin. So these are supernova, these are asteroids, these are variable stars, and we already have classification pipelines for it. This is, getting closer to being like a solved problem for classifying, is it this type of supernova or that type? But to go further, actual astronomers would take, the catalog of supernova and analyze, individual ones with code, making different plots, comparing them to papers to see if the supernova is actually scientifically interesting. We don't have a way to automate this at this stage. And we also don't have enough astronomers to give that sort of in-depth analysis treatment to everything coming from these pipelines. And so this is something I'm actually quite excited for going forward, because this is probably, I'm not saying it's going to be astronomer level, if we throw GPT-5 at each, analysis of supernova, but it's certainly better than anything we've had before for comparing it to, stuff that we've seen in papers to determine if one particular supernova is scientifically interesting to the community.
Yeah, and I've been involved in various citizen science
Yeah,
projects,
exactly.
and and I remember the discovery of like green pea galaxies or Henny's Vorwerp, that a non-scientist, but just like a human being with a human brain, was able to look at huge amounts of astronomical data and go, here's a thing. Has anyone ever seen these before? Do we even know what this is? And then the astronomers go, no, we don't know what that is. Let's do some follow-on observations. And I think that feels like, we're going to get this gigantic data set coming from Vera Rubin, and and that in those data, there must be things that are happening, less commonly. Like supernova are common, but weird double supernova. There's a story we report on just this week in Universe Today about a kilonova supernova that was probably some kind of combination object that was super weird, very rare.
Yeah, that's cool.
And you want to know before anyone else that this thing might have been seen, and try to get people starting to know about it. And so it's almost like you're looking for those moments that's unusual, that can then begin a line of inquiry.
Right. Yeah. And I think citizen science has been insanely valuable for this. Like, as you said, if the green peas and the Vorwerp galaxies, this is a perfect example of, human insight at scale where, professional astronomers, we just can't do that. And so the humans or the volunteers have made all these amazing discoveries. And so I think that this is also, going to stick around, and volunteers are going to be absolutely, indispensable when we have these massive amounts of data coming in for identifying this.
How much of the compute resources allocated to Google and ChatGPT would you like it to be shifted over to this kind of scientific discovery? 90%?
Yeah, this is
85%?
a fantastic question. So in the long run, I hesitate to make predictions past 10 years, but sometimes they're really fun. In the long run, I think that as these models get better at science, and this does seem to be a big focus for some of these, labs, either in industry and also in academia, is to, actually get them to, as we've discussed the whole interview, make more, or actually be able to make discoveries and contributions to scientific literature. So if we reach this, I think that we should probably be allocating a huge amount of compute. A huge amount of these data centers being built could be allocated to scientific discoveries. Automating these data analysis at large scale to actually try and come up with new medicine, to more material science research, because these will have practical implications for society, and it could greatly improve quality of life if we can actually get these language models to discover a better solar panel, or a better treatment for a particularly rare disease. I think this is going to probably be our best use of compute going forward. And so I would love to see 90%.
Yeah.
Or more.
It's funny because we hear like DeepMind has a real research focus, and they're trying to provide these tools to researchers. OpenAI has said that they're putting all this, they really feel like that's the real purpose. Like what they want is science.
Yeah.
But as a person who had to pay the API costs, did you experience this sort of incredible enthusiasm from the companies to help you do your science?
Yeah.
Are they knocking down your door to help you just analyze Vera Rubin data?
So I I would love them to provide me the
Yes.
cost to go ahead and run, these pipelines on all of their Rubin and analyze all the supernova. And, you best believe I'm going to be reaching out to them for covering these costs. I have gone like
It's weird that they haven't already reached out to you, though. This is what
yeah,
I'm
well,
saying.
it's a great question. I think there's just so much going on in the space that you might be right. Like it's hard to keep track of everything. In previous projects that I have been involved in, for example, last summer I presented one where I evaluated how good the coding language models are at solving physics problems with code. So, like analyzing data from a gravitational simulation of stars orbiting each other, you can ask it questions like, what is the period of the orbit, or we can modify gravity and see if they can understand how we modified gravity in the simulation. And so we did reach out then to these companies, and they actually provided us they were able to cover the costs of evaluating models, which is pretty great. So they are pretty open at and they have a lot of different academic grant programs. And so this is stuff we will be applying to once we, show that it can actually, if we can show that it can lead to discoveries, I'm hoping that they will be happy to contribute.
Nolan, what are you obsessed with right now?
Yeah. So I am really obsessed with actually putting everything that I've said to the test. So we're dreaming about, as we said, language models that can actually, we can integrate them into pipelines and they can look at every supernova and image coming from these telescopes. However, to actually put that to the test, I'm very curious if, as of now, I've had them write descriptions, but what if I give them the ability to write code, to write Python? What if I don't just give them the image, also the observations from different telescopes or, tabular data, what we know about the distance? And so if they can write code, they can make whatever plots they want. They could even incorporate, simulations, for example, to analyze this data. And with this, and also with the ability to read literature, we turn these into not just single call language models, but actually like agents, in the sense that they have all these tools that to actually do a much deeper analysis. And you could imagine like in the future, we might have a Wikipedia page for every supernova, a Wikipedia page that comes from these pipelines, and also all the analysis that our agents did on them, which would be much better evidence for seeing if it's interesting than just saying, oh, I looked at the image and it looks like a new discovery.
Right, but it could like look at the image and go, I think I see something. I'm going to check the infrared image to see if I still see the same thing. I see some differences. I'm going to run a plot to get a sense of what this is. Like the kinds of things that an astronomer would actually do as they're starting to go down the question of whether or not this is useful and interesting. I sort of think back to when James Webb first came online, and we got a lot of people saying, we found the most distant object.
Yeah.
But that wasn't real until they'd done the spectroscopy on it. And so when they finally did the spectroscopy, then they were able to make claims that, yes, indeed, this is indeed the most distant object that we've ever seen. And you could imagine the LLMs having that kind of scientific basis and going, wait a minute, let's not jump to any conclusions. Let's draw on more tools and let's keep going. I'm going to request some time on Chandra, and the new Chandra 2 is automatic and goes, you got it, boss, and turns to this object and makes the required observations. Like it'd be super weird if some of the stuff starts becoming more automated all the way through the pipeline.
Yeah, this is definitely, I mean, especially as you said, like requesting time on a telescope. Like this would be next level.
Yeah. Yeah.
But I see it as a possibility. And so, yeah, this is what I'm obsessed with testing right now. So in order to see if they can actually do this, is it actually going to be useful? That's the issue. Like they can call Python, it can, analyze data from multiple telescopes, but can it do it correctly? I have to go out this year and actually develop systematic benchmarks to see if they're actually doing the correct things, and develop a system that can actually ace these benchmarks, these tests.
And is your instinct, and like I know this is a very kind of useless thing to say, but is your instinct that they will be able to figure this out And it's just a matter of the right framework, the right training, the right
Yeah.
benchmarks and feedback, or is it like we're going to run up against no, these things are kind of dumb actually.
Yeah. So this is what there's a concept of jagged intelligence, which is essentially the fact that these language models might be incredibly good at proving a math problem. Like they won IMO gold, the math Olympiad. However, I have a number of tests where I can show them like not a spiral galaxy, literally just an image of a hand-drawn spiral and ask, is it clockwise or counterclockwise? And they're unable to do this. They're unable to, for example, read time off of an analog clock, which, I guess might be difficult for some people now also. But the language models, there's something in the architecture where it encodes the image in order to understand it, that it loses some information to actually be able to read these analog clocks. And I found cases for this in science too. And so it's quite difficult to know what they actually can and fundamentally can't do without testing it. And this is a huge problem, and this is why we need to actually go out and benchmark them. But I would argue that if there is tasks that are very easily verified, for example, like I said, proving that a discovery is actually a discovery is really hard to verify. Like you might require follow-up time on a telescope. However, stuff like proving a math problem is a bit easier because there can be automated ways to show, the easiest one is just checking the solution doesn't match the answer key. And problems like those, you can actually train the model to do. And they can get, I'm pretty confident they can get good at it. And so there's cases like this, potentially cases like this in astronomy too, and also cases of the former where, since it's so hard to verify, it doesn't look like they're going to be extremely good at them. Right off.
Yeah. I mean, that matches my experience with like coding challenges and things like that, where sometimes it's able to do the thing that you're asking for it. And then other times it's not able to do the thing that you're asking it to do, or it screws it up in a very predictable way. And it's you on the person who's interacting with the LLM to go, to just like stop asking for the things that it's bad at and only ask for the things that it's good at. Right. Like you're the one driving this for now. And so you have to understand the purpose of the tool and see it as the hammer that it is and not as the multi-tool that you're hoping that it is. And I think, we're going to get that place in astronomy. And I guess right now, there isn't enough people trying these experiments yet to find out. They've either done some minor experiments and then abandoned it, or are sort of living in this sort of fantasy land and they don't actually know what it can and can't do.
Yeah. And actually, I think this is a much more general advice that if I have any advice to provide, this would be it, is to actually just try and use these, chatbots and language models a lot more to actually, and this is the only way that you're going to understand what it's good at and what it's not good at. And this is how they can actually be quite useful. For example, you can find that they're actually good at retrieving information from some part of the web. And so you'll use that more, but they might not be good at reading images of clocks. And so whatever the equivalent of this is for, stuff that you do on a daily basis, you need to try the models to actually find out what those are. And this is, huge.
I 100% agree with you. That's absolutely my experience as well. Like down to the level now, like where we're coding and I will be like, I know what you're going to do and don't do it. Right.
Yeah, exactly.
And I just don't ask it for those kinds of requests because it's going to just predictably mess it up.
Yeah, totally.
Yep. Awesome. Well, no, absolute pleasure to talk to you. Good luck with your work. I can't wait for this future automation where robots are crawling through all of astronomical data and finding every interesting anomaly.
Yeah, thanks so much, Fraser. And I really hope that can actually work out. We're going to put it to the test and see how useful it can be. But you've had great questions. So hopefully I've provided some, good perspective on how these language models can be more than just chatbots.
Well, hopefully other astronomers will be reaching out shortly.
Yeah.
That's how you know it worked.
Great.
Thanks.
Thanks so much.
I hope you enjoyed this conversation with Nolan Koblischke. Now, we had this main conversation about sort of large language models and the system that he's built. But really, this is in service to his actual astronomical focus and interest, which is in studying tidal tails that are surrounding galaxies like the Milky Way and using those as a probe for dark matter. Because, as a galaxy is torn apart, the galaxy orbits multiple times around the galaxy and leaves a tail behind that is a probe to let you map out the shape of the dark matter gravity that is coming from that galaxy. And so he's been thinking a lot about how the work on getting robots to classify images can feed into the kind of research that he wants to do. And so we talk a lot about sort of how we can identify these features in galaxies and what kinds of interesting discoveries could be made to help us learn more about astronomy. So that longer version of the interview is available over on Patreon. It's available ad-free. You don't have to become a member. You can just watch it right now. There's a link down in the show notes below. Go watch it over there and see the additional stuff. And then just remember that we always produce these longer versions of the interviews, and they're free to watch. You just have to go over and follow us on Patreon. Now I'm going to give you some final thoughts, but first I'd like to thank our patrons. Thanks to Abe Kingston, Barry Lake Roofing, Brian Bode, Carrot Chuck Hawkins, Commander Bailock, Cy Nielsen, Dark Finger, Dave Veribuff, David Gilton, David Matz, Evan Pro, Greg Feely, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Josh Schultz, Marcel Smith, Michael Purcell, Nordspace, OneStepForAnimals.org, Paul Robach, Ring Kaidu, Richard Williams, Sean Sargent, Stephen Fowler Munley, Team 49, Telescopes Canada, and Wolfgang Klotz, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So this is sort of a thing that I am obsessed with right now, which is like, how do we use these large language models for good and not for evil? Because there seem to be a lot of downsides. Now, potentially, there's going to be some upsides, and who knows, maybe they will make all of our lives a lot better. But I think there's going to be a lot of people using this technology sooner than they should for ways that they probably shouldn't, and that we're going to suffer the consequences in terms of people losing some of their critical thinking skills, in terms of electricity that should be used for other purposes going into powering these things, the economic issues, people potentially losing jobs, and so on and so forth. And I am like a big advocate of the need for science to be able to continue to progress. And that, I think what we see from the companies is this, they say that the goal is science. And yet the facing side that we experience is these chatbots, or them creating characters that you can interact with on various platforms. And no thanks. I want the science. And so anyone who is thinking of interesting scientific uses for this technology has my attention. And so I'm really glad that Nolan is thinking about this, and I'm going to keep my eye out for more of this kind of thing. And hopefully we will be able to send those signals back to the companies, to the funders, to the governments, that, really the place for this is to help us progress as a society. All right. We'll see you next time.